Hello, welcome to CSC7132, Operating Systems and Networking. This is Brady Chen. Now, in the previous section, we discussed the paging. Now, paging resolved the issues of the external fragmentation. Now, by using the pages, each process going to be divided into a small block called the pages, and each page will be loaded into a frame in the computer memory. Since these frames don't have to be in the same location, so this actually resolves the external fragmentation issue. However, paging has its own drawback. One of the problems is the performance is not really that good for the paging. Now let's actually discuss this in much detail. And also, to resolve the problem with the paging, we actually introduce another, approach. It's called segmentation. Now let's see what's the problem. What's the issue with the paging? Okay, we know that for any programs or program component, they might have several components. One is the code, right? And then the statical data and dynamical data. Okay, so now I use different code to represent this. The code I use blue color, and then I use green for the statical data, and I use purple for the dynamical data. Okay, so that's a program. It contains a couple of components. Okay, now using the paging, I need to actually divide the program into pages, right? So let's say here's the first page. Okay, and then here's the second page, third page, fourth page, and then I use another page which contains the leftover code. So that's page 0, and then page 1, page 2, 3, and 4. I have a total of 5 pages. Okay. Now, in order to load this program into the memory, physical memory, I need to find 5 frames, right? So let's see. Here's the frame. Okay. So then I'm gonna put the page 0 into frame number, let's say this particular frame, and I put the page 1 into this frame because this frame is available, and page 2 into here, and the page 3 over here, and the page 4 at the bottom. So I find the 5 frames over here. Okay. So basically I map page 0 to, page 0 to this, page 1 to this, right? And the page 2 to here, page 3 over here, and the page 4 at the bottom. Okay, so let me actually delete that one. That one doesn't exist. So I'm also gonna, color it. So page 0 is the code. Now, page 1, it contains half code and then half statical data, right? And what about page 2? Page 2 contains half of statical data and half of dynamic data, the heap or stack. And page 3 is completely the dynamic data, right? And page 4 contains some dynamic data. So when I execute the program, so let's say I start to execute the program starting from the logic address 0, and then I start to execute the program. And at a certain point, I need to call the statical data, right? So I execute some of the code over here, and suddenly I'm going to call the statical data. So then I'm going to jump to here. So then after run a couple of instructions, I'm going to jump to here. Okay, because when I actually jump from page, this is in page 0, and then here it's in page 1, right? It's in page 1. So I'm going to actually jump to here. And then I come back, continue. Okay, so I come back and continue. Once I actually pass the instruction from page 0 into page 1, now in the physical memory, this is going to actually jump from here all the way to here, right? Now once it's complete, and then during the execution, I may actually access some data over here. So you're going to see that in the computer physical memory, the CPU going to actually fetch the instruction over here, and then jump to here, and then jump back to, this particular frame, and then jump here, jump to here. So you're going to jump back and forth, even though logically these codes are very close to each other. But in the memory, they're scattered all over the places. So this is not really efficient. So the segmentation is trying to solve the problem. So a segmentation is a variable size block of a logical address space identified by a single number, the segment number. Okay. Now we're dealing with segmentation, not paging. Okay. So in that case, I can pretty much define, say, the code as one segment, and the dynamic data as another segment, and statical data as another segment, dynamic data as another segment. So then I can put together all the code in the same physical location in the memory, put all the statical data in the same physical location. Or even in the code, you may have a couple of subroutines, functions. I can put functions in one function in the same memory location, another function in another physical location. So I actually allocate the memory based on the logic components of the code instead of the process, instead of the like equal size page. Okay, now this is just like when I try to move my furnitures. Now here I have a bed, I have a cabinet, I have a desk. So these different furnitures have different sizes, right? So in that case, using the paging, the moving company gonna say, okay, so we use paging, okay, so we are gonna provide you a couple of boxes. All the boxes have the same size, okay. If your furniture can fit in one of our box, that's fine. If you cannot fit, you cut the furniture into pieces and put each piece in the boxes. So I'm gonna move the boxes, and then we can assemble the furniture, after actually move the furniture to the other location. That's paging. Now with segmentation, I'm gonna actually divide the program into a logic component. So that means if these piece of code belongs to the same part, then don't separate them. Okay, don't cut them and put one in one page, put the other piece in another pages. This is just like the moving company saying, okay, in my case, I'm gonna move the table as a whole. I'm gonna move the cabinet as a whole. I'm gonna move the bed as a whole, instead of cut the furnitures into pieces and put each piece in the different boxes. That's the idea of segmentation. So now let's take a look at this. Now here we have two processes, process 1 and process 2. Okay, now process 1 has 3 segments: the code, data, stack. And process 2 has 2 segments: code and data. Okay, so then when I actually when I load the process into the computer physical memory, so I load the code in one memory location, data in another location, and the stack in another location. But I do not separate each segment. Okay. So for the code, for process 2, the code is going to be in this location, and data going to be in the same location. Okay. Still, we don't have to, find a hole to put the whole program, all the program components in the same hole. I still can actually put a different piece of code into different memory location, like a code I put over here, and data over here, and the stack over there. Okay, I still do that, and each segment has different size. That's the difference between the segmentation and the paging, because when I actually do the paging, all the page sizes are the same. Okay, now if the operating system actually use the segmentation, then how does the operating system manage these, the programs and the memory? So instead of using the page table, I use the segment table. So that's a segment table 1, that's a segment table 2. Now what do I need to have to manage this segment table? Let's take a look at that. Now here's the example of using the segmentation. So in a logic address space, the program contains 5 logic components. One is the subroutine, and I call it segment 0. And the segment 1 is a function called square root, okay, SQRT. And segment 3 is a stack. And then the main program is segment 2, okay, so that's the main program. And then symbol table, that's segment 4. So I have 5 segments. Now here is the segment table. Now this is segment number, and for each segment, the size defines the size of each of the segment. Okay, so for example, segment 1 subroutine, the size is 1000. Okay, so and then segment 1, the size is 400, so that's 1000, that's 400. And then segment 2, that's 400. Segment 3, that's 1100. And this segment 4, it's 1000. Now, once I allocate the memory location, then I have a starting address, SA. Okay. So for example, it's a 1400. So in the physical memory, so basically this segment 0 is allocated to the starting physical address 1400. Okay. And segment 1 starting address is 60. Okay. And then segment 2, that's in here. Okay. And segment 3 over here. And segment 4 over here. 4700. That's a starting address. So that's the reason why I need the starting address and also the size, or sometimes called the limit. So that basically defines the, which segment is in which memory location. So once I have a starting address and then I have a size, this basically tells that this segment is going to actually start from 1400 all the way to 2400, because 1400 plus the size. 1400 plus the size. Okay, so 1400 plus the size, which is 1000. Just this gave you the limit. Okay, the upper bound for this particular segment. So again, like for segment 3, the size is, starting address is 32. Okay, 100, and the size or the limit is 1100. So I add this, I got a 0034. So 4300 is the limit for segment 3. So that's the segmentation table, the segmentation approach. Now here, let's talk about how can we translate the logical addresses into the corresponding physical address using segmentation. Okay, so the operating system translates logical address of the form SW into corresponding physical address. So suppose that's a logical address. Now the first part is the segment number, and the second part is the offset. Okay, so let's see. Based on the segment number, we look at the segment table, and then we find out the size of this segment and the starting point of this segment in the physical memory. So here's the physical memory. So the starting point of this segment. So this is a segment S, and if I want to see, here's W is the actual logical address in this segment W. Now here's, I want to find out what's the corresponding physical address for this W, right, in the logical address space. So the segment table basically tells you the starting address, so SA. This is where this segment is located in the physical memory. And the size basically tells you the size of this segment, right? So basically, so that's the size. Now, if W is greater than the size, greater than or equal to the size, so that means this W is not in this segment. This W is more, it's outside this segment. Okay, so we just say this W is illegal. It's not in this segment. Okay, otherwise, we're going to add the W to SA, because this W basically tells the location of this address to the beginning of this segment. Okay, so now we're going to add W to SA. So SA plus W, this is going to give you the physical address for this. Okay, corresponding to this logical address. So this is how we're going to actually do the address translation using the segmentation. Thank you.